And so I didn't want to assume that y'all just from the notes would understand how to do the solubility sphere. Um, yes, we could use the HSPIP software, but I think it's pretty instructive to do it yourself in Excel to kind of see, the nuts and bolts of how it's calculated. All those formulas from the notes are put in here, but you may want to correct a few. So let's go through those formulas just to make sure that yours match mine, because um, I want to make sure that your spreadsheet works, and I had to tweak this one a little bit. So I'm going to zoom in on this. Specifically, I'm going to go look at RA. So let me zoom in. And so what I'm going to do is I'm going to left justify this. You don't have to worry about doing this, but I'm going to do it so that I can get the formula to show out to the right. Okay, so here's our beautiful formula for RA. And notice the anchoring. We're anchoring the substance that we're testing, that apiazine grease. So C8 is anchored, and it is subtracting C10, which is the acetonitrile. Now, the order doesn't matter because we're going to square it. So if we had C10 and C8 swapped, it wouldn't matter because we're going to square that. Also, look at the use of parentheses. I know one of you showed me a spreadsheet earlier. The parentheses were crazy. So this is the minimum number of parentheses that you need. You could take that squared quantity, multiply by 4. Where'd that 4 come from? Well, remember in Hansen space, the D parameter is multiplied by 2. And so we have 2 inside the square. If we square that, we can pull it out and make a 4. So that it's 2D minus 2D. And so the 2's squared will come out as 4. And then we have the difference in P value. That's the column D, D8 minus D10. And then the E8 minus E10 is the H value. And we square those differences, add them up, and then take the square root. So that's the RA value. I call that the Hansen distance. The reason I don't call it the Euclidean distance is because of that factor of 2 on the D value. So it's unique to the Hansen solubility parameters. So I've coined the term Hansen distance. Even asked Charles Hansen if he was okay with that, and he said, I'd be honored. So, so that's great.
We're recording, right?
Pardon?
We're recording?
Yes, we're recording. Mm-hmm. And so then, you copy that down, you get on here in the corner and double click, and it'll go all the way down, paste that formula. That's why you want to anchor it, because if you don't anchor it, then it will screw up when you copy it down. This cell reference will move down. Now let's look at the relative energy difference. Okay, in the spreadsheet you have, I think it still has the RA formula in there, so I just went ahead and changed it. Let me change again the justification on these real quick. Okay, so that's anchored. The R0 value is in the denominator, and it's anchored because we want to copy this down and we want to keep that R0 reference. And we're just looking at the distance RA compared to the radius of the sphere. And this will tell us if it's outside or inside the sphere. So if it's greater than 1, it's outside the sphere. If it's less than 1, it's inside the sphere. And that sphere radius is R0. And so if you've got that simplified formula, go ahead and hit enter and copy that down. Then let's look at this one. This is very simple. R0 minus RA. So we have the anchored R0 value minus the RA value. We're going to calculate this column mainly because we need to use it in the fit function. So this just simplifies our fit function. You could...
Our spreadsheet has it flipped.
And that's okay. I went ahead and changed it because up here in the title it says RO minus RA. So I wanted the formula to match what the title was, just to be sure. Yeah. That was one of the things I changed for sure. So then questions? Please ask. Let me cut those. Can you cut those lights, the middle switch? And that way it'll be a little easier to see to get rid of the glare. Is that better? Yeah. Okay. Okay, so I'm going to hit enter on that, and then I'll copy that down. Then this solubility one, I just wanted to go by the scores. This is a new formula. It's not in your spreadsheet. What I wanted to do was be able to put in what numbers were inside the sphere. So let me come up here and type in inside. And so once you go up to that J7, K7 line and put inside and then put 2 in K7. Because we've scored these interactions on a 1 through 6 scale, and which is good, which is bad. This is the column where we decide what is a good solvent, what's a bad solvent. And so we need some criteria. We have these scores, 1 through 6, for the interaction of these solvents with this grease. Some were 1s, which meant they pretty well dissolved it. 2s were, it looked kind of like it was dissolved, but you could still see a clump at the bottom. 3, the solution was murky, and the grease looked like it changed form a little bit. Maybe it softened, but didn't really dissolve. 4, the grease blob looked like it did in the previous pictures. It might have some murky water, so something's, or murky solvent, but essentially the grease hasn't been appreciably swollen or softened. And so anyway, we have these different scores, and we need to decide which one of those scores is going to be inside the sphere. What are we going to call good? So at this point, we're going to say 2. Any score of a 2 or a 1 is inside the sphere. So I just made an if-then statement. So this might be new for you, is an if-then statement in Excel. Okay. And so I'm looking at G10, which is my score. So if, open parenthesis, and then you have the conditional statement. So if G10 is less than, and I don't want to say less than my inside score because my inside score is 2 and I want to include 2. So I need to add 1 to that. So I'm going to say if it's less than the sum of 2 plus 1. And these are integers, so it's going to capture 2. I'm just doing a little trick to make sure I get 2. So it's another way of saying less than or equal to. Be sure to anchor that K7 value so that when you copy it down, it doesn't move the reference. And so this is the conditional, the logical test, it says. And then you have a comma, and then you have the value for that cell if it's true, and then a comma, and the value of that cell if it's false. So this is a really great tool in Excel. You can do if-then statements and conditionals, and you can, find a million ways to use if-then statements in Excel. They're really great. So I will use them a lot. And so this, I'm saying 1 is a good solvent and 0 is a bad solvent. And that's what this formula will give me. So if it's a 2 or less, then I'll get a 1 in this column. We could test that. Like if I made this one a 2, then this value should become a 1. Yeah, and it did. So I'm going to do undo for that because I don't want that to be a 2. Okay. And we can come down here, we can see there's a 3, and of course it doesn't get captured. So now that's saying that DMF is a good solvent, DMSO is a good solvent, and N-methylpyrrolidone is a good solvent. So those are our 3 good solvents for this. And we're going to try to fit a sphere around all of these. Okay, so then our predicted, this is based upon the RED value. If it's less than 1, then it's a good solvent. If it's not less than 1, it's a bad solvent. So we have this is being predicted by the location of our sphere and the radius. So this is not dependent upon our scores. This depends upon the sphere coordinates and the sphere radius. So it's just seeing if the sphere coordinates and radius match our prediction. Match our claim as to good and bad solvents. So this is the predicted column predicted by our model of the sphere location and the sphere radius. And our scores generate the sol question mark, the solubility question mark, saying is it a good or bad solvent.
And the scores are qualitative.
Yeah, our qualitative subjective judgment. And so that's one of the criticisms of the Hansen solubility parameter system is that scoring the interactions is subjective. So there's really no way around that in that you just have to come up with what we call good operational definitions. So what's the definition of a 1, 2, 3, 4, 5, and 6? the more specific you make those, the better the system. And so you need to decide, what are you going to call a 2? What are you going to call a 3? And it's iterative to some extent. You may look at the interactions and you say, well, here's my full range of interactions. These 3 were pretty strong, so I'm going to call that 1, 2, and 3, and then 4, 5, and 6. So then you need to write your operational definitions as to what your judgment was, and then you can expand your range of solvents and use those definitions to get a better feel for the full cloud of solvents. Okay, so I'm going to copy that formula down, and then we have the fit function. So it's also an if-then statement. And so we're looking at L and K. So if the prediction equals our subjective, determination of solubility, so if a 0 equals a 0, then we're good. So the predicted matches our scores. And if the predicted doesn't match our scores, we need to calculate how bad the fit is. Okay. So if they match, whether it be a 1 or a 0, that's fine. You get a 1 for the fit function. If they don't match, then you calculate this sort of figure of merit. And so this is going to be, again, if it's a very small difference between RO and RA, so the solvent's very close to the radius, like if it's a bad solvent and it's inside the sphere, if it's close to the edge, that's not as bad if it's right in the middle. Right? So this is an exponential dependence upon how bad the situation is. If you've got a bad solvent in the middle of your sphere, then it's going to wreck your fit. And if you have a good solvent way far out of your sphere, so R0 is this long and the RA is that long, that's a big difference, and it's an exponential dependence. It gets worse and worse the farther out that good solvent is from the radius of your sphere. So we want Excel to hate that situation and move the sphere in that direction. So it's like a magnet, a tractor beam that pulls the sphere over to the good solvents. Okay. So that's our fit function, and then we have, those are the different components of the fit function, and then up here we have the product of all of those. So all of those multiplied by each other raised to 1 over the number of solvents we have. So it's to a fractional power of the count of solvents. So the 1/20th root.
What happened to 122, the N-methyl
22. Oh, this one right here. It's, if I were to bump out the decimal places, let me make it scientific notation. That'll do it. Oh boy.
Oh.
Let's see, which way is he going? Yeah, so it's 10 to the minus 4. So it's it's not quite in the sphere. It's only out by 10 to the minus 4. So it doesn't pass the logical test, but it's so close that that exponential dependence upon that distance is e to the 0. And so e to the 0 is 1. So that's a good question, though. It just failed the logical test, but it wasn't too bad. Yeah. So what we're going to do is let's make our radius small. So let's make our fit bad. So let's make a radius of 2. And I typically do this. I'll make a really small radius, and Excel will move the center of the sphere around to get between the 3 good solvents. So it'll put the sphere in between the 3 good solvents. And then I'll expand the radius so that I capture the good solvent. That way I'm not shoved around by the bad solvents. We can play around with this a couple of different times.
Fit values didn't change.
On yours, the fit values didn't change when you changed R0? Uh-oh.
We have different numbers for RA as well.
Oh, maybe your scores are different. Okay, let's check our scores. So for acetonitrile, you have a 5. 4 for acetone. Acetophenone, 5. You might not have 1s here and here. Dimethylformamide is a 1 and sulfoxide is a 1. Okay, then ethyl acetate, 4, 4, 4 for those 3. And then we have water is a 5, hexane's a 6, isopropyl alcohol is a 5, MEK is a 3. N-methylpyrrolidone, do you have a 2?
I have a 3.
Okay, make a 2 for N-methylpyrrolidone, just for the purposes of today's class. Yeah.
It did change.
Okay, good. And then the 4, 4, 5, 4, 5, 3, 4.
But only for that one, the DMF and DMSO are still ones.
There's still ones? Okay, just because I've done solver already and you guys haven't. So let me go ahead and let's put in,
Yeah.
so let's pick some initial guesses. So let's look, these two solvents are good. They're 17 and 18. So let's make this 17.5. That way we start at the same point.
Okay, yeah.
And then here's these are 13.7, roughly 14 and 16. So let's make this one 15. And this is the hydrogen bonding parameter is between 10 and 11. So let's make it 10.5. Okay, so I've pretty well satisfied those two solvents. Not exactly, but you see the NMP one is pretty bad. That's our fit value there, 0.093. But anyway, we've got an initial guess. So that's how you come up with your initial guess. So that's a good thing to talk about. So you've got your solvents, you've scored them, and you've got to come up with an initial guess for the sphere. And so I just pick a couple of solvents that are good, and I'll put the sphere location, I'll start out in between those two good solvents. And I'll start out with a small radius, and I'll run solver one time. And it'll move that center of that sphere around to get in between the three good solvents. So you have these numbers now, the 0.741. Okay, good. So we're all on the same page. Now let's do solver. So come up to the data ribbon, and here's the solver tool. You click that. You should get this dialog box. And so we have an objective cell. That's our fit value. We want that to be 1. So we click that cell here, and then we say we could make it a max, we could make it a min, but we want a particular value. We want it to be 1. I don't know why I put 0.99999, so let's just go 1. All right. Okay, that's right. And then over here, by changing cells. So solver changes those cells and looks at the fit value. It does what we could do by hand, but it's a lot faster than we are. So I'm going to eventually, I mean, you could make it do all 4, but I'm just going to do the DP and H values and change the radius by hand for now. Okay. So I'm just going to pick DP and H for those 3. So it's going to change DP and H and to make the fit value 1. It's probably not going to be able to because the radius isn't going to capture all 3. But let's see what it does. So I always got to get a look at my fit value, 0.875. Let's see what happens when we hit solve. 0.925. So it got better. Now it says solver could not find a feasible solution. There's no error there. It's just saying you asked me to get to 1 and I couldn't do it. Okay, so that's not a problem. If it did go crazy, you can hit cancel and it'll go back to what it was, but you got to run solver again. But sometimes you think, oh no, it screwed everything up. Just hit cancel and it'll undo itself. Yay. Okay. So let's do the POV Ray now, just to see what everything looks like. So we don't have a perfect fit, but let's see what it looks like. So I'm going to shrink the screen a little bit. And up here is a solubility sphere code. So I'm going to get these 4 values first. And you may need to go download that POV Ray file. It's the one that says popular cleaning solvents.pov. I think that's the one that you'll have. And when you double click it, you should open POV Ray and you should get, this really scary looking code. Yeah. Okay. And so then if you come down here, it's like at the lower part of the first, top of the page, here's the sphere, location, colors, transparency, etc. will be added later. So you go to your Excel sheet, you get these four values, hit Control C, go to the POV Ray code and paste it over those 4 rows. And so that'll update the D, P, H, and R0 value. So that's going to draw the sphere for us in POV Ray. Then scroll down here to the bottom part of this file, and you see this comment area, the solvent DPH data points. All of the following code block is generated in Excel to save time. Simply delete this code block and paste in the cells from Excel. So we're going to select these spheres, sphere rows, and I'm going to go to Excel and select them here. So I have them selected in Excel. Control C. Questions? Is this working for you? No? Okay, one second. And then we go to POV Ray and hit Control V and it pastes over those. Okay. Then I'm going to select the text data labels and I'm going to go over to Excel and select them here. I'm going to hit Control C in Excel, go to POV Ray and hit Control V. So it overwrites all of those. It's tricky to do the selection with the, touchpad, I'm sure. And so you might put the cursor in there and hold Shift and do down arrow. And that's a little easier than trying to use that touchpad. So just to show you, I'm doing the same thing now. I've got my cursor right here for the cylinders, and I'm going to hold Shift and go down arrow, and I'm selecting all of those. And then I go over to Excel, and I want the cylinders. So I'm going to select the cylinders in Excel. I could again do the Shift down arrow on this one too to select them all. Control C in Excel, go over to POV Ray, Control V. So it's tedious, but it's not as tedious as going in and editing those values by hand. Okay. Now, what really changes? The solvent coordinates don't change, the labels don't change, and the cylinders don't change, but the colors of the solvents and things change, whether they're good or bad. So that's all we're really changing in POV Ray. Is if you'll notice over here, the good solvents, most of them are glass ruby, but occasionally there's a glass green in there. And that's the color of a good solvent. And so the reason we're updating the spheres and the text and the cylinders is because we're changing the colors of those values based upon if Excel calls them good or bad. Yes?
So the green labels in POV Ray, I have data labels and then below it the drop lines. So the cylinders is what goes under drop lines?
Yes, cylinders are drop lines. They drop down to the baseline. So
I have a green line in mine that says cylinder and then like the line with pigment color. So like paste over that for mine.
I've been grabbing this out of Excel and copying it and then pasting over the whole thing in POV Ray.
Until the above code block is generated in Excel?
So here's the cylinders. Are you talking about the cylinders?
Yes.
Okay. Here's the cylinders, and then I go over here to POV Ray, and it's the drop line cylinders. There's cylinders up here. These are the Cartesian box that go around to make the frame that we're plotting in. So don't ever overpaste those. Just paste over the drop lines.
So paste over everything in POV Ray up until the above code block is generated in Excel. There's a couple lines of green text.
Yeah, right here. Everything below these lines is what you're replacing. Does that make sense? Okay, very good. And then we can come up and do run. Run is the rendering. And you should get this. Yours may look a little different because I fiddled around with the reflectivity of the planes in the back and the bottom. But you can see over here on the back side is NMP, and up here is DMF, and DMSO is kind of obliterated by the sphere, but it's in there as well. But notice how the sphere does not contain NMP, and if we looked at it carefully on the back side, we would see it doesn't contain DMF. We could look at Excel and see what it does contain because the RED value would tell us, if if it's less than 1. So it definitely contains DMF. It does not contain DMSO exactly, and it doesn't contain NMP. So that's the sphere. So we can increase the radius until we get all of those inside the sphere. Did everybody get this picture? No?
I don't know. We have all version of already.
Okay, let me come look. So it will not load. Let's see, where's that? Did you double click the, how did you get this screen?
This one right here.
Okay. What you should do, I see that, but let's, this is just the installation features. So go to Blackboard here and download the download this, okay, and double click it so that it will load it into POV Ray. So if you download that file, double click that, and load it into POV Ray. Okay, so the error that, I won't use your name, the student got, was it didn't have the include files for these glass values. And so yes, that could happen. A lot of this code is calling things out like glass, ruby, and so on. And let me just show you the POV Ray features. Whenever you install POV Ray, in your whatever your My Documents folder is, and like on the campus computer, your S drive contains your profile documents. It's going to put a POV Ray folder in there. And so under My Documents would be POV Ray. And if you look inside there, you have the version number for the folder, and then you have these different folders. And one of them is called Include. And these are libraries. So these are libraries of functions that you can call out. And one of them is glass. And so this has all the definitions for the different types of glasses that are used in POV Ray. So I'm going to open this in Notepad and just show you. It's just a text file that contains all of these little definitions. And so it's declaring, like we're using glass ruby, I think. And so color ruby, and this is giving us the RGB values for what they say ruby is. Okay, so you can, and then green glass is here, and there's the RGB values for green. We really don't necessarily need this. We could define all of this in our own document, but I just, when I made this, chose to use the glass library. And so when you loaded it, it said, I can't find the glass library. And so you would just need to, in POV Ray, go in here to there's some ways to fix it and I can teach you, but you want to just include those. One way to include them is to open them. And so if you come to File, Open, you can go and open that glass and include file. You go to where we just were, you go to My Documents. Come on. My Documents, POV Ray, 3.7, include, and then you would just open that glass, include file. And by opening it now, POV Ray has access to all those glasses. And then we can call them in our file. So, we have all of these different ones, color glass ruby, color glass green, and we're using those in our definitions of our solvents.
Can you change the color?
Yes. And so then if you wanted to come up here and play around with that, you'll find those definitions up here where I describe what a good solvent is, what a bad solvent is, and so on. Actually, I defined it in Excel. Up here it says good solvent is cold glass green, non-solvent is cold glass ruby. And if I change them here, then they change in all of the code for the spheres, the cylinders, the text, and so on. So that's a pretty useful thing to know, because some people are particular. If you can't really see through the sphere, then you want to change it.
I've got the. I ran it and it worked this time,
Okay.
but my good solvents are that see-through blue that you can't really read.
Yeah, so you might make them a little darker. So let's find a darker glass value.
Okay.
We'll go to the glass file and see what our options are. We have a dark green.
For good.
Yeah, so you might try instead of, so it's underscores, cold glass dark green with underscores in between them, and they're capital, so it is case sensitive. So I'm going to put a dark in here, D-A-R-K, and an underscore. So that's dark green, and it changed my good solvents to dark green.
Glass underscore.
It's going to be a real tedious video.
It's gonna what?
Be a real tedious video. Watching other people do Windows is murder. Okay. So I'm going to go ahead and take my spheres and start copying them over there. So I find it easy just to replace all of them than to try to find the ones that changed. So I'm going down here to the spheres. Control V from Excel. Then I'm going to change the text because I have the text change color too. Those people who are familiar with using the HSPIP database are probably pulling their hair out, because it does the sphere for you and it's real time, and so you don't have all of this. I've just gotten really used to the way my plots look, and so I don't mind doing this. But if I'm in a hurry, I'll use HSPIP because it's definitely worth it. Okay, so I've replaced those. Let's see what our dark green solvents look like. Let me go back. Since I Okay, so yeah, they're much more visible. So there you can see that NMP is down here. And I opened it with a different program so I can zoom in. I have DMF inside the sphere and DMSO, like right on the edge, I think, or vice versa. In front of us, in front of the sphere, is ethyl lactate. Up above is IPA or isopropyl alcohol. Acetone is down here to the right. Acetonitrile, propylene carbonate. So you can see what solvents, might be. Like we could look at ethyl acetate or ethyl lactate and see if it really was a bad solvent or if it was close, and so on. If I wanted to blend a couple of solvents, a blend of acetone and IPA would get close. So that would be better than either one individually. So that's the power of the Hansen solubility parameters, is I can understand how to blend solvents. If they came and said, I'm sorry, you can no longer use DMF or DMSO. And you say, well, can I use isopropyl alcohol and acetone? And they said, yes. Well, then I can make a blend of those two, and those might be more safe for the workers, environmentally friendly. There's a lot of other factors that come in. Now, one more thing that's handy in Excel. So go back to Excel. And I love this feature of Excel. And that is conditional formatting. So I've got all of these numbers, and I would like to color code them based upon good or bad. Okay, and really our RED value, you know, if, or the distance. I guess we could do this. Now let's do the RA value. So again, if it's a low RA value, it's good. If it's a high RA value, it's bad. So we sort of have a, I mean, not really, but almost a continuous scale for RA. So I'm going to select RA, and I'm going to click on the home ribbon. So selected RA and a home ribbon, and I come over here to this wonderful little drop down, and it's called Conditional Formatting. And I like the color scales. And so I can make the high value green and the low value red, but I don't really like that. I like the low value to be green and the high value red. And so I click this one, and it color codes my RA values. Isn't that beautiful? So my lowest RA values are green and my highest RA values are red. And so this is a green to red scale for my good and bad solvents. And this would be ideal for your tables. You know, let's say you're not going to do a sphere, but you're going to just do RA values. Then do the conditional formatting, and you can visually see, wow, these are the good solvents, these are the bad solvents, these are the most promising interactions, these are the bad interactions. Or if you're doing material compatibility, right? You're worried about this being compatible with that. Maybe it's the opposite. Maybe far away is good because you don't want to have your gaskets dissolve in your solution. So, or your gloves. Maybe you want the RA of your solvents to your glove material to be as far away as possible because you don't want the solvent going through your gloves. And so in that case, a big RA value would be green and a low RA value would be red. And so the red solvents would be dangerous for you to use with those gloves because it would go through the glove. So in this case, we want low RA values, and sure enough, it found our two solvents, the DMF, DMSO, and N-methylpyrrolidone. Now these numbers, these RAs, are based upon our DP and H values. And so, you know, this is going to be more useful after you use Solver, or if you have, like I said, the glove example, if you have the Hansen solubility parameters for that polymer up here, then this would be the RA of all of those solvents to that polymer. And you have to decide whether, you know, interaction is desirable or interaction is not desirable, depending upon which way you make the green and red scale. Okay. Is that helpful? Yeah. Have you used conditional formatting before? No, it's nice, isn't it? It's just really very, very nice. And so you can also put in other value functions. I have RA, in some of my spreadsheets, I'll use RA to tell me if this solvent is going to clean this particular soil. But then I might have the flammability of that solvent ranked in a column, and I might not want it to be flammable. So if it's flammable, it's red. If it's non-flammable, it's green. And then I might have the toxicity of that solvent in a different column. And there, if it's toxic, it's red. If it's non-toxic, it's green. And then I just look across the table and find the row that has the most green in it. And in fact, I could take these different values, toxicity, flammability, global warming potential or ozone depletion potential, and some interaction score based upon RA, and I could have 4 or 5 different criterion, and I can multiply those by each other so that I get if it's favorable is say a 1 and disfavorable is 0, then the closer everything is to 1, the better. And so I can multiply all of those by 1 and multiply them by each other. And if they're all 1s, they stay a 1. But if any one of those is really bad, then it knocks it out of the list. And so then I have this result column that's green to red, 1 to 0. And that's how you can find the solvent that satisfies most of your criteria. It's not as toxic as the other one. It's not as environmentally damaging as the other one. It interacts well, maybe not the best, but you can rank the different features and come up with this desirability rating, and you can really see it with the conditional formatting, and then you can do some tricks like this, like we did with this fit function, to where 1 is good, 0 is bad, and you can multiply things by each other and get this overall sort of not necessarily risk assessment, but desirability rating and pick the best solvent for your situation. So I think that's a useful skill to know. POV Ray is fun for visualization. We could do the same thing with the HSPIPs. So anything you want clarification on, because we've got about 5 minutes. Yes?
In my case, I use only 4 solvents, so
Okay.
I should use all 20 or
Well, what are you doing again as far as the solubility?
for glutamic acid and folic acid.
Yes, you've made the precursors for those, yeah.
Yeah.
And you have the 4 solvents that it's not soluble in, right?
I did yesterday.
Okay.
So folic acid dissolve in ethanol and glutamic acid dissolve in DI water.
Oh, okay. Wow. All right. So, you know, pretty much all of your solvents are going to be above in the alcohol region. Yeah. So we'll just visit specifically. So maybe bring me your data and we can look in my office and look, and I'll give you some ideas of what to go next, where to go next.
Can we stop recording?
Yeah. All right.